Consider how a United States Navy warship could sink under the enemy flag, only to be recovered by its original fleet, renamed and deliberately blasted to the seafloor by American rockets. That is the exact paradox of the United States ship Stewart, officially designated Destroyer 224. This vessel endured a mechanical and operational trajectory unlike any other hull in the Second World War. To understand why it became an archival ghost, we must track the exact mechanics of its triple demise. The stakes were absolute historical erasure. If the final coordinates could not be isolated, a United States Navy destroyer known for having served under both American and Japanese flags in the Pacific War would remain a half-verified legend. The first rupture in its American career began with combat damage and then became a dry dock disaster. In 1942, Stewart suffered damage during the Battle of Badung Strait and limped into a floating dry dock in Surabaya, Java. As the dock lifted the ship, the keel block support failed, dropping Stewart off its rests and causing severe structural damage and partial flooding inside the repair basin. With enemy forces advancing rapidly on Java, the United States Navy had zero time to attempt a complex heavy salvage operation. The immediate operational decision was absolute. American and Allied personnel disabled the wreck to keep it from being used, and dockyard workers scuttled the dry dock with Stewart still trapped inside before the port was abandoned to the advancing Japanese forces. That should have been the final mechanical state of Destroyer 224. However, the Imperial Japanese Navy evaluated the sunken wreckage and determined the hull possessed enough structural integrity to warrant a massive salvage effort. They pumped the flooded compartments, patched the blasted steel, raised the ship, and executed extensive structural modifications. The vessel was completely integrated into the enemy fleet and redesignated as Patrol Boat Number 102. Operating deep behind Allied lines, it created a bizarre operational anomaly. Allied pilots began reporting impossible visual sightings of an antiquated four-stacker American destroyer sailing under the Japanese flag. These intelligence reports spawned the legend of the Pacific Ghost Ship. The second recovery happened at the end of the war. In 1945, occupying American forces found the battered hull tied up in a Japanese port, and Navy personnel reclaimed it as DD-224 without a name. In a nod to its survival, American sailors affectionately referred to the vessel as Recovered Allied Military Personnel, 224. But the hull was completely obsolete, heavily modified, and thoroughly worn out. The final institutional decision was to strip the ship, decommission it, rig it for scuttling, and send it to sea as a post-war target and burial at sea. On May 24, 1946, the ship was towed off the coast of Northern California to serve as an aerial and naval target. The structural resilience demonstrated during this final destruction sequence was staggering. The old warship absorbed aerial rockets, machine gun fire, and naval gunfire, refusing to go down easily. Contemporary accounts describe the stubborn hulk enduring the exercise before finally rolling to port and slipping beneath the surface. That final plunge initiated a new, quiet erasure. For 78 years, the exact resting place of the wreck remained unconfirmed. The final towing coordinates from 1946 were notoriously imprecise. Without accurate global positioning data from the era, the target zone was merely a vague estimation off the coast. The primary limit for modern historians was this severe coordinate inaccuracy. Finding the ship required stepping backward into the paper trail. Researchers isolated the original logbooks from the exact tugboat that towed the battered hull out for its final target practice. By matching compass headings, towing speeds, and recorded times from those decaying pages, historians managed to calculate a theoretical endpoint. This was the critical knowledge gain required to even attempt a physical search. They synthesized the archival math into a defined search area, yet knowing the approximate location on a piece of paper did not solve the physical reality of the ocean. The ship had vanished beneath the Pacific, leaving researchers decades later staring at a massive, completely blank coordinate grid. Hunting a target in the deep ocean requires overcoming an absolute legal and environmental firewall. In August 2024, a specialized expedition team arrived off the coast of Northern California to execute a highly regulated search. They were not looking for a shallow coastal wreck. The calculated target zone sat above a seafloor plunging to a depth of 3,500 feet. At this extreme vertical drop, the ocean imposes a massive physical barrier. Sunlight cannot penetrate. The ambient pressure destroys standard structural housings. Conventional human diving was out of the question, so the search had to move into robotic systems. The environment itself denies direct access, forcing any search effort to rely on complex engineering solutions. But the crushing depth was only the first barrier. The expedition faced a rigid jurisdictional firewall that strictly governed every operational decision. The designated search area fell squarely within the protected boundaries of the Cordell Bank National Marine Sanctuary. Within this sanctuary, NOAA strictly regulates seabed disturbance and activities affecting historic resources through permit controls. Furthermore, because the target was a formally commissioned naval vessel, it remained the perpetual sovereign property of the United States government. Under the Sunken Military Craft Act, the entire site was protected by strict federal law. The law does not consider the hull abandoned. It remains a legally recognized entity of the state, shielded against unauthorized interference. This dual legal framework dictated the entire survey strategy. Under the approved permit approach, the team avoided anchoring, dragging hardware, recovering artifacts, or sampling material from the wreck. The operating rule was practical as much as legal: map the site without disturbing the vessel, the surrounding sediment, or the sanctuary floor. Despite these severe restrictions, the researchers achieved a critical operational milestone. Working under approved federal permits, they surveyed a search area reported at roughly 37 square nautical miles. This box translated the archival paper trail into a practical ocean search boundary. Establishing the specific grid was a vital knowledge gain. It gave the surface team a defined theater of operations where they were legally cleared to conduct non-intrusive mapping. The survey vessel had to sweep every inch of this specific zone while guaranteeing absolute non-disturbance. That rule eliminated traditional salvage mechanics. In a standard offshore operation, engineers might lower heavy clump weights to stabilize a camera sled in deep currents. Inside the sanctuary, even a slack cable could become a permit violation if it touched bottom. Every device in the water column had to remain fully controlled, leaving almost no margin for error. The mission was a joint execution by Ocean Infinity, SEARCH, and the Air Sea Heritage Foundation, in collaboration with NOAA's Office of National Marine Sanctuaries and the Naval History and Heritage Command. Their institutional decision was to treat the search as a non-intrusive archaeological survey. The first phase relied on untethered acoustic systems to cover the grid at speed, while any closer inspection would still have to remain remote and non-disturbing. The entire operational design was built around avoiding physical interaction with the protected zone. This legal reality shifted the engineering burden. The team had to find a specific metallic structure inside a vast geographic box under thousands of feet of water, using a robotic architecture capable of operating in complete darkness. The survey plan compressed the work into a 24-hour mapping window. That narrow window immediately eliminated standard single-unit survey techniques. Dragging a single tethered sonar array back and forth across the grid would have been far slower and would have introduced more cable management risk in a protected water column. The engineering team recognized that speed and absolute precision had to scale simultaneously. Their operational decision was to abandon the linear search method and implement a simultaneous swarm deployment. The expedition utilized 3 completely untethered autonomous underwater vehicles operating concurrently. These robotic units, designated as Huygens 6000 systems, are designed to endure extreme oceanic pressures while executing pre-programmed geometric flight paths. Dropping 3 heavy machines into the water column simultaneously introduces severe navigational hazards. They must not collide with each other or strike the physical boundary of the marine sanctuary. To manage this risk, engineers staggered their search patterns, effectively dividing the vast grid into distinct overlapping sectors. This swarm scanning architecture allowed the team to achieve complete, high-resolution acoustic coverage of the massive target zone without dragging a single physical tether through the protected water column. Deep underwater, optical cameras can work only at close range with artificial lighting, making them unsuitable for the initial wide-area search. The initial search therefore depended on high-resolution sonar, including synthetic aperture sonar, flown from the autonomous vehicles. As the three vehicles flew safely above the seafloor, they emitted precisely timed acoustic pulses and converted the returning echoes into a detailed acoustic map. Operating three autonomous vehicles at massive depths introduces a hard technological limit. Because the robotic units are completely untethered, there is no physical cable connecting them to the surface vessel. Water is an incredibly poor medium for transmitting high-bandwidth data. As a result, the engineering team could not receive real-time imaging feeds or instantaneous mapping renders. During the autonomous survey phase, the operators on the surface had to trust the program logic, monitoring only basic acoustic telemetry until the vehicles returned and the stored data could be processed. That limitation applied to the first search phase before the later ROV inspection gave the team live visual confirmation. The simultaneous deployment progressed continuously through the night. The three vehicles executed their precise grid sweeps, laying down parallel tracks of acoustic data across the 37 square miles. Each seafloor change, geological outcropping, and metallic anomaly was logged onto the internal hard drives. The robots maintained strict altitude discipline, ensuring they never breached the zero-touch mandate while gathering millions of acoustic data points. When the search clock finally expired, the autonomous vehicles received the command to terminate their patterns and ascend to the surface. The physical recovery of the units marked the end of the data acquisition phase and the beginning of the diagnostic phase. Deck crews hoisted the heavy robotic systems aboard and immediately extracted the sealed digital modules. The engineers transferred the massive files into the shipboard processing computers to compile the overlapping tracks. The entire 24-hour blind search hinged on whether the sweeps had caught a solid return amid the endless miles of empty mud. Acoustic data can reveal structural identity when deep water visibility is limited, but it does not have to stand alone. When the surface computers rendered the files retrieved from the depths, the empty topography of the ocean floor yielded a sharp metallic anomaly. Translating the raw acoustic data into a geometric model revealed a vintage destroyer hull of the right size and form, largely intact and resting nearly upright on the deep seabed. That posture provided an immediate knowledge gain. It fixed the wreck's orientation and showed that the primary exterior hull survived the 3,500-foot descent with remarkable cohesion. Because the hull did not invert during the descent, enough of the exterior profile remained exposed for sonar and later robotic visual inspection. The result was a well-preserved but damaged structure, not a pristine wreck. However, finding an old destroyer did not automatically prove it was the precise target. The ocean is vast, and many decommissioned hulls were used for post-war target practice, so the team needed a layered identification process rather than a single acoustic clue. Investigators matched multiple traits at once: the hull size, the Clemson-class form, the search position, the known Japanese modifications, and the later ROV imagery transmitted from the seafloor. American engineers originally designed this class of destroyer with 4 distinct smoke funnels, a classic 4-stacker silhouette known to every sailor in the pre-war fleet. When the Imperial Japanese Navy rebuilt Stewart in 1942, the refit altered that profile with a trunked funnel, a tripod foremast, and Japanese armament changes. By the time the wreck was inspected, the sinking exercise had damaged the superstructure, toppled the mast, and smashed the Japanese trunked stack, making the identification problem harder. The combined acoustic and visual records still aligned: a largely intact Clemson-class hull in the expected location, carrying the scars and altered architecture consistent with Stewart's 2 Navy history. Yet external remote mapping establishes a hard-proof ceiling. The high-frequency sound waves required to generate such precise exterior resolution cannot fully reveal the condition of sealed internal spaces. Because physical penetration of the wreck was outside the scope of this non-intrusive survey, the expedition team faced a real forensic limit. The structural integrity of the internal bulkheads, the condition of sealed engineering spaces, and the exact flooding sequence remained unverified. The external acoustic and visual data confirmed that the main hull survived in largely intact form, but they could not fully explain the internal mechanics of the final sinking. After a prolonged sinking exercise, investigators might have expected extensive detached wreckage across the surrounding seafloor. High-velocity ballistic impacts can shred unarmored bulkheads, sever masts, and tear apart upper deck structures, while a damaged vessel's final site formation can vary widely depending on structural condition and flooding paths. In Stewart's case, the evidence pointed away from a large mid-water breakup, without requiring a dramatic outward explosion or miles of debris. However, the wider grid made the contradiction measurable. This debris field scarcity provided a crucial clue drawn from what the survey did not show. The lack of a broad scatter of off-hull wreckage is consistent with a sinking sequence in which the vessel remained largely coherent from the surface to the bottom. It suggests rather than proves that the heavy steel structure avoided a catastrophic breakup in the water column and settled onto the seabed as a mostly intact hull. That limited debris pattern raised the next analytical problem. The external surface of the remaining structure was difficult to interpret. The ship endured a relentless barrage of explosive impacts before it finally slipped beneath the Pacific surface. But it also sat immersed in a highly corrosive, high-pressure saltwater environment for almost 8 decades. The distant acoustic mapping revealed a battered, degraded, and severely compromised exterior. Differentiating the exact cause of every twisted deck plate and collapsed bulkhead introduced a severe operational problem known as target strike overprint, in which corrosion and pressure damage obscure the mechanical signatures left by military ordnance. Resolving this target strike overprint would normally require forensic sampling that the current rules did not allow. In a marine investigation where intrusive sampling is authorized, structural engineers could collect small sections of damaged metal for laboratory analysis. Microscopic examination of fracture surfaces, corrosion patterns, and deformation could help separate sudden impact damage from decades of slow marine corrosion. That work can narrow the cause of damage, but it rarely turns a complex wrecking sequence into a single simple answer. Under the approved permit, no steel sampling was authorized or conducted. The researchers could not retrieve deck plates, cut test sections, or inspect fracture surfaces in a laboratory, so the physical forensic investigation had to halt at the outer edge of the remote record. The robotic sweeps and ROV inspection documented what could be observed without disturbance, leaving only the question of the wreck's future management. What is the final status of a sovereign ghost ship that will never be touched again? In traditional maritime engineering, locating a submerged target and mapping its physical dimensions serves as the immediate precursor to physical recovery. The discovery phase normally transitions directly into the mobilization of heavy lift vessels, specialized cutting tools, and complex extraction operations. But the operation to locate the specific destroyer fundamentally breaks this standard industrial sequence. Identifying the exact coordinates of the vessel did not initiate a salvage queue. Instead, it confirmed that the wreck would be managed as a protected, sunken military craft within a national marine sanctuary. The successful completion of the remote mapping marked the end of this expedition's physical engagement with the site. It was a survey and documentation phase designed for heritage management. The present management condition of the site is protection in place. The United States government bars unauthorized disturbance, artifact recovery, and commercial salvage under the Sunken Military Craft Act. Authorized agencies can permit narrowly defined activity when the law allows it, but protection remains the default. Because the site is managed in place, the massive dataset gathered during mapping serves a different institutional purpose. The expedition achieved its primary survey objective, a high-resolution environmental and structural baseline for future heritage management. By recording the hull's present dimensional state, researchers created a detailed digital anchor point for future comparison. This baseline allows long-term observation through repeated remote surveys. Future teams can return to the exact coordinates, execute comparable sweeps, and overlay new models onto the current data to measure the rate of deep-sea decay. They can also monitor structural collapse and track the heavy metal as it settles deeper into the soft ocean floor. All of this critical forensic observation can be executed while strictly maintaining the untouched integrity of the sovereign site. The legacy of this uniquely traveled warship is no longer defined by its unusual operational trajectory across enemy lines or its immense endurance under heavy target fire. Its final operational phase is one of perpetual, untouchable stewardship. The naval authorities and marine sanctuary administrators now hold precise coordinates and survey data to support long-term heritage management. The site will be protected through regulation, permitting, and future remote observation. The paradox that opened its story now has a fixed position on the chart. The ghost ship has been found, its identity verified through combined acoustic and visual evidence, and its final resting place documented for protected stewardship.